This is Chen from Nanjing University. In this talk, we will talk about how model benefits input generation in testing systems and how to build a layered model for complex systems. Software testing, or finding inputs to manifest bugs, is an old problem. It's analogous to finding stars in an extremely huge universe. Generating effective inputs has challenges. The inputs should be syntactically correct. This is the easy part because complex systems may have simple input formats like systems and key value storages. The hard problem is that we should generate inputs that are semantically valid, and these inputs should be diverse. We will talk about them in detail next. We can either randomly sample inputs in the whole space or mutate the existing to generate new inputs. The fuzzing is the most powerful tool for complex systems nowadays, but it may get trapped in a local region easily because it does the local search and generate inputs may be similar. On the other hand, sampling is able to see the entire space, but since most inputs are semantically invalid even they are syntactically correct, it's easier to sample invalid inputs like hitting the vacuum in the universe. In this paper, we present a better sampling with models. Models specify which inputs are valid or not. That is, it constructs an input space. There are no invalid inputs. In this way, we can avoid sampling invalid inputs and guide sampling or even guide fuzzing. For example, a file system model should specify that before opening a file, it must exist in the system. But consider that there are much more other complex system calls and obscure parameters. It's difficult to build such a model. So in practice, building a process model for real systems is intractable because they are too complex and support too many features. We find that the evolution of software may serve as hints to build models for complex systems. Complex systems are just like aircraft carriers. There are many components in it, and these components interact with each other, so the system is too complex to model it directly. But actually, not all aircraft carriers are such complicated. The first aircraft carrier was just converted from a collier by adding daggers and some other simple components. Then it evolves into the concurrent complex one. So if we are modeling the first aircraft carrier, it's much easier. Again, let's move forward. The first aircraft carrier is also developed from other simple shapes, so modeling these shapes also becomes easier. Analogously, complex systems are also developed from original versions by adding various features. So we can model the original systems, but we are testing the complex ones. So how can we bridge the gap? The answer is the evolution. Since we can model the original system, we can build a simple and process model for it first, and use this model to sample inputs. These inputs are valid and diverse, and they target the fundamental functionalities of systems. Then, similar to the evolution, we can refine these inputs to manifest other various features of the system. Since these features are hard to model precisely, the refinement is relaxed as long as it keeps the correctness and diversity that are produced in the simple model. First, we build a simple model, and in this model, sampling semantically correct and diverse inputs. Then we refine these inputs to manifest other system features, but at the same time, we should preserve semantically correct and diverse generated in the first model. And at last, we have a syntax model which refine inputs into syntactically correct ones. We implemented this approach into testing file systems. First, we have a core model which organizes file structures, that is, the fundamental functionality of all file systems. The state can be represented as a structure graph, and we use a stateful model checker to generate diverse inputs. Second, we have a core extension model, which refine these inputs to manifest other file system features like channeling, caching, and still it preserves states in the core model. At last, we have a syntax model. It just refines the inputs into syntactically correct. Let's take an example to see the whole generation. This input crashes F2FS and can be generated by our later model. First, we need a complex file structure. There is a directory with depth 5. In core model, we generate many inputs result in diverse structures, so the core model is able to generate such a structure. And at the same time, we need plenty of I/O operations which may manifest file system channeling, caching, or other features. The core extension model manifests these features and provide high-level system calls. Finally, the syntax model views random parameters, and these parameters may trigger other complex file system features. We developed a prototype tool named Dogfood and evaluated it with different checkers to see whether it can benefit these checkers and detect real file system bugs. We choose 6 popular file systems like ext4, betafs, which are provided in the Linux kernel. In the first experiment, we compared Dogfood with Zscaler. Both of them tested in a 12-hour running, and we found that Dogfood was able to find hundreds of crashes much more than Zscaler. We report some of crashes as bugs to the developers, and some of them were fixed quickly. In the second experiment, we compared Dogfood with Ace using a crash consistent checker. Each of them generated 1,000 inputs to the checker, and we can see that Dogfood helped the checker detect much more issues, and it benefits the checker a lot. Finally, let's make a summary. We see that finding inputs to manifest bugs in software testing is an old and difficult problem. And a model may offer surprises sampling such inputs, but in practice, building models for complex systems is intractable. And we found that the evolution of software may serve as hints for building layered models, which can help generate inputs. The experiments show the power of our layered models. Thank you.